Hello and welcome back to another Calculus 3 multivariable calculus video. Today we will be going over directional derivatives. So briefly, I just want to talk about exactly what a directional derivative is, and essentially what a directional derivative is taking the secant line between two partial derivatives and a singular point. If we can do that, then we'll essentially calculate the slope at a specific area or in a specific direction. So, like I talked about briefly a couple videos ago about partial derivatives, a partial derivative is essentially when we hold the y or the x constant and derive in terms of the other that is not held constant. So, in the x direction, we would be holding the y constant, and in the y direction, we would be holding the x constant. That is essentially what a partial derivative is. And for a directional derivative, if we took two partial derivatives at specific points, that little red point there on our little graph, that would be our two partial derivatives at that point. And if we had another point, AB, if we just took the secant line between those two, that would be our directional derivative. So that's essentially what a directional derivative is mathematically. So I guess the why we're doing this is it's a little bit difficult to explain mathematically, but just a brief explanation is it's a steepness. It's a steepness in a specific direction. That's something that I'll get deeper into in the next video when we talk about the gradient, because these two are essentially they're essentially one in one in the same almost. I like to think of it. Maybe that isn't technically true, but I like to think of it that way. So I guess the directional derivative, why we're doing this is think of a real world application wherein a company is trying to build a winding road up a hill. We don't care about the slope of the hill. We care about the steepness and the slope along the path of that road, right? So that's kind of what the directional derivative is to me. Just think about that as a real world example. I'm just going to briefly write that down here. When we have, it's, let's see here. It's essentially just, I'm going to put this in quotes here. It's essentially steepness of a road. Not the hill. I'd say that's kind of the easiest way to think about it in a real world application, pretty simply. So I guess we understand, we want to know how now. Well, there's a theorem. I'm just going to go ahead and write it down here. We have the directional derivative in the direction of the vector u of f of ab. That is going to equal the vector with the partial derivative of x at that point AB and the partial derivative of y at that point AB multiplied or taken the dot product by that vector u, that direction u. So what is this essentially saying? This is essentially saying that we're computing the instantaneous rate of change of our f of x, y at a point AB in the direction of this vector u. So notationally, that's what it is. One big note that I really want to make clear here is that this u must be a unit vector. If you do not recall what a unit vector is, it is essentially dictated by that little hat there, and we have this vector u over the magnitude of that vector, and that'll essentially give us our formula for what a unit vector is. That's something that we talked about in Calculus 2. If you need a refresher on that, go ahead and briefly catch yourself up on that. Shouldn't be too difficult. We all pass Calculus 2 if we're in this class, right? So I guess let's just go ahead and get into an example. Our example given here is z is equal to 100 minus 2x squared minus y squared at the point P 3, 5 with the vectors u, root 3 over 2, 1/2, and vector v, negative 1 over root 2, 1 over root 2. And we are asked to find the directional derivative of our f at the point 3, 5 in the direction of u, and conversely, directional derivative of f at 3, 5 in the direction of v. So how are we going to go about doing this? Well, first of all, I want to come back to our note over here of u must be a unit vector. So let's just go ahead and make sure that these are unit vectors real quick. Unit vector is when the magnitude of these vectors that we have here is equal to 1. So let's just go ahead and make a check. Check. Okay, well, let's go ahead and take the magnitude of our vector u, which is going to be the square root of root 3 over 2 squared plus 1/2 squared. We should just be able to know this. This is just equal to 1 by our unit circle, but let's just go ahead and show the work. Root 3 squared is going to be 3, and 2 squared is going to be 4, plus 1 squared is 1, 2 squared is 4. So this is just going to be the square root of 1, which is going to equal 1. So therefore, this does work out. Our vector u is, in fact, a unit vector. Let's go ahead and do it for our v now, which is going to be the square root of this vector here, negative 1/2, 1 over square root of 2, plus 1 over square root of 2 squared. Same thing. Let's just go ahead and do the algebra here. We have 1 squared is 1 over 2 squared is 2, plus same thing over here. 1/2 plus 1/2 is going to equal 1. Square root of 1 is equal to 1. Therefore, we have 2 unit vectors. So we are good to use both of these vectors when finding the directional derivative. So let's go ahead and refer back up here when we have this formula where we have a vector of the partial at AB of x and y respectively. So let's go ahead and calculate our partial derivatives there. So we are going to calculate now. So calculating, we can just go ahead and do this real quick. We have some f sub x is going to equal the partial derivative of f of, let's see, what is our function up here again? 100 minus 2x squared minus y squared, I believe. Yeah. Holding everything else constant other than our x, we are just going to have negative 4x. That is our f sub x. I will evaluate that in just a moment at our point. Our f sub y is going to be the partial of f with respect to y of our function, 100 minus 2x squared minus y squared. That is going to equal negative 2y, holding everything else constant. So now we are going to plug in our point P. So negative 4x evaluated at our point P. Negative 2y evaluated at our point P, which is going to equal, what was that, 3, 5, I believe? Yeah, 3, 5. That's going to equal negative 4 times 3. That is just going to equal negative 12. And we have negative 2 times 5, which is going to equal negative 10. Therefore, our first aspect of this is going to be negative 12, negative 10. So we now have the gradient. That is something I will get to in the next video, but I'm just going to call it that right now. So we essentially have found, we'll do blue for this one, we have found this. And we have our vectors given to us over here, so we have u and v. So simply our du, our directional derivative in the direction of u at our point 3, 5 is going to equal negative 12, negative 10 times, or taken by the dot product of our vector u. So that's going to be times root 3 over 2, 1/2. Conversely, we have our other directional derivative that we were asked to find. directional derivative in the v direction of our function at 3, 5 is going to equal the same thing, negative 12 and negative 10. The dot product of, let's see, what was this? Negative 1 over root 2, 1 over root 2. So just taking, I'm actually going to split these up. So now simply taking the dot product, something that we are very familiar with, we have negative 12 times our root 3 over 2 plus our negative 10 times 1/2. So we are going to have negative 12 root 3 over 2 plus, what is that, just negative 5. That'll just be negative 6 root 3 minus 5. I am not going to simplify that further. That is our directional derivative at the point 3, 5 in the direction of our u vector. Same thing over here. We're going to take the dot product. So we are going to have negative 12 times negative 1 over square root of 2 plus negative 10 times 1 over the square root of 2. This is just going to be, negatives cancel out. That's going to be 12 over the square root of 2 plus, no negatives cancel out, so this is going to be negative. Negative 10 over square root 2. Same base. We can just go ahead and simplify this into 2 root 2, which is just going to equal 2 root 2 over 2, which is just going to equal root 2. So those are our directional derivatives in the direction of u and our v vectors. Pretty simple process. I am going to be introducing a shortcut almost in the next video, or something that we could conceptually think of. So I'm going to be essentially introducing the gradient, which, just a brief explanation, that this right here actually has a name and is called the gradient. So I'll get more into it in the next video. Just understand that that's what the next video will be talking about. Main takeaways from this is what a directional derivative is in the real world. It's the steepness of a road, not the hill the road is built on. And the main note that I want to make is that our u, or whatever the direction is, it must be a unit vector. Otherwise, this will not work. Or you could divide by the magnitude at the very end, mathematically speaking. I wouldn't recommend it. If it isn't a unit vector, you could do that. Wouldn't recommend it. Just might as well get it out of the way first. Check that first, because otherwise, if you forget it, then let's just say you'll be getting the question wrong. That was the directional derivative. Next video, I will be getting into the gradient. Thank you very much.